Hello everyone. In this part of the lecture on the step response of the systems, we are going to focus on the response of the second order systems. So basically, a second order system is a system which has two poles located in the S-plane, let's say, and it might have there might be zeros coming with it as well. But for now, we assume that there are no zeros. And our second order system could be illustrated in the form of a transfer function with b over s squared plus as plus b. So over here we assume that the DC gain of the system is equal to 1. And there are no zeros. Later we will discuss the effect of having additional zeros for our second order system. So based on the values of a and b, which appear as the parameters of the system, the poles of the second order system may be located in different situations as we will discuss in the next slide indeed. Okay. However, you should also keep in mind that compared to the first order systems, the second order systems exhibit a wide range of responses. Okay, so their response is not as simple as the first order systems, let's say. We know that in the case of first order systems, that you know the response, and as you change the location of the pole, the response will keep its general shape indeed, yeah? But it might become faster or slower. But in the case of second order systems, depending on the location of the poles, the overall shape of the response might be changed as well. And of course, the speed of the response might also change. Alright, so as I mentioned, we assume that we have a unit DC gain and there are no zeros for our system. We can illustrate our second order systems in the form of b over s squared plus as plus b of b, and as the input to the system, we are assuming the unit steps. So r of s is equal to 1 over s, and then we are going to figure out how the c of s, or the output of the second order system, will look like. Before we start, we can check this fact that the derivative of c at time 0 plus will be always equal to 0. Regardless of the values that we have for a and b. And you can find it by this theorem that we have. Limit of d of c of t over dt as t goes towards 0 plus could be replaced by the limit of s times sc of s, which is dct over dt indeed, as s goes towards infinity. And for c of s, we have c is equal to g times r, or b over s squared plus as plus b times 1 over s. If you replace them, we will end up with 0 as the value. And we also assume that prior to time equal to 0, the output value was already equal to 0. And since the time derivative of c at 0 plus is equal to 0, we will start the step response with a slope of 0 right at the beginning. For the second order systems, we will have 4 cases. The first case will happen when we have separate real roots. You can see an example over here. For g of s, we have 9 over s squared plus 9s plus 9, which gives us two poles at minus 7.854 and minus 1.146. So this is called an overdamped system. And the type of the step response that we get for such a second order system will be in this form. So c of t will be equal to 1 plus the coefficients times e to the power of minus 7.854, and minus another coefficient times e to the power of minus 1.146 times t. And you should also see that these values at the exponents, they come from the poles. So depending on where the poles are located, we will have these exponential terms in the step response of the system. And the general shape that we have for such a system will look like this that you can see over here. Since the DC gain of the system is equal to 1, the final value that we get for such a system will be equal to 1. You can see that here we have the starting point with the slope of 0. So the derivative of the response at t equal to 0 plus is equal to 0. And then the rest of the response is somehow similar also to the one that we had for the first order systems. Then we have the second case, which is called as the critically damped system. And it happens when we have multiple poles, or indeed two poles, since just a second, or indeed two poles, as we are dealing with the second order systems. You can see an example here at the same place. We have two poles at minus 3, and the example that we have for such a system is s squared plus 6s plus 9 at the denominator and 9 at the numerator. The terms that we have for the step response are in the form of 1 minus a coefficient times t e2 minus 3 minus e2 minus 3. So the exponential terms that we have here both are in the similar form, t e to the power of minus 3t, e to the power of minus 3t, but one of them is multiplied by t. Okay, so that's why it is different than the previous case. And in terms of the shape, it is still similar to what we had for the first order systems, but a bit different at the same time. The main difference is over here, where we have 0 for the as the value for the derivative of the response at the time equal to 0 plus. The next case is when we have the underdamped systems. In the case of underdamped systems, the two poles that we have for the second order system will be located in the S-plane in the form of a complex conjugate roots. They will have the same negative real value. So you can see as an example here that we have two poles here and there. The real value that they have is equal to minus 1, and in terms of the imaginary value, one is plus j square root of 8 and the other one is minus j square root of 8. And the transfer function is 9 over s squared plus 2s plus 9. In this case, the general form for the step response is in the form of 1 minus e2 minus t. So the coefficients for t over here for the exponential term comes from the real value over here, minus 1, times a cosine term plus a coefficient times the sine term, times t. We need to have t here. And it could alternatively be written in the form of 1 minus a coefficient times e to the minus t times a cosine term. You should also pay attention to the value here, square root of 8, which comes from the imaginary part of the poles. And these kind of systems are called underdamped systems. You can see the general form or general shape of the step response, which has the final value equal to 1. It starts from 0 with the slope of 0 at the beginning, and then it goes beyond the final value of 1, which is here. There are some oscillations, and then it eventually ends up at 1. So we have some, at the beginning of the response, there will be some oscillations, and then it will settle down. These kind of systems are called the underdamped systems. And finally, the last case which we have for the second order systems is called the undamped systems. In the case of undamped systems, there will be two poles on the imaginary axis. The example that we have here is 9 over s squared plus 9 for the transfer function, which means that we have two poles at plus j3 and minus j3. In this case, there is no damping. That's why the system is called undamped. We will have oscillations starting from 0 with the slope of 0 right at the beginning, and then there will be oscillations going forever. The general form for the step response comes in the form of 1 minus cosine of 3t. And again, you should pay attention that this 3 comes from the imaginary value that we have for the poles. So these are four cases that we have for the second order systems. You can see the general shape and general form. Later we will go into details of each case one by one, but for now we just take into account the general form, okay? In the general form that we have, assume that we have a unit DC gain. G of S is illustrated in the form of B over S squared plus AS plus B, as we just already had. We just defined two new parameters. One is called the natural frequency, and the other one is called the damping ratio. Natural frequency, or omega n, is defined as square root of B. And that's indeed the frequency of oscillations when A is equal to 0. So when A is equal to 0, we had the undamped case. You can see here that at the denominator we have A equal to 0, because if it's in the form of S squared plus AS plus B, you see that A is equal to 0. And then we had B equal to 9. B was equal to 9, so omega n, which is equal to square root of B, is equal to square root of 9, and it's equal to 3. And that's the frequency of the oscillations, as we had in that example. The next parameter that we define is called the damping ratio, zeta. And it's indeed the ratio between the exponential decay frequency and the natural frequency. Natural frequency is omega n, and the exponential decay frequency is A over 2. If we replace omega n with square root of B, we will get A over 2 square root of B. So this will give us the zeta. And then we can rewrite G of S in the new form. We replace A and B with omega n and zeta. And therefore we will have G of S equal to omega n squared over S squared plus 2 zeta omega n S plus omega n squared. Alright, and then we can have this classification of the second order systems based on the value of zeta. For the case of undamped systems, zeta will be equal to 0, and this is the case because we have A equal to 0, and for zeta we have A over 2 times square root of B. Therefore zeta will be equal to 0 as well. And then we have undamped system. Then we have the underdamped case. For the case of underdamped system, zeta will be equal to 0 and 1. When zeta becomes equal to 1, we will have the critically damped case, and when zeta goes beyond 1, we will have the overdamped. So based on the value of zeta that we have, as zeta, let's say, increases from 0 to 1 and beyond, right at 0, we will have the undamped. Then between 0 and 1, we will have the underdamped. Right at 1, we will have the critically damped. And beyond 1, we will have the overdamped case. Over here, we have three examples, G1, G2, and G3, in the form of transfer functions. And we need to find out the zeta and report the kind of the response that we expect. Let's go through the first one. So for G1 we have 12 over s squared plus 8s plus 12. If we compare it with the general form that we have for the second order system in the form of omega n squared over s squared plus 2 zeta omega n s plus omega n squared. For the first case G1, omega n is equal to square root of 12 and 2 zeta omega n is equal to 8. This could be written in the form of 2 square root of 3. Therefore, zeta will be equal to 8 divided by 2 omega n, or 8 divided by 4 square root of 3. So we will get 2 over square root of 3, or 2 square root of 3 over 3. So if we get the exact value for this, we will have the final value for zeta, and based on that we can say that that our second order system belongs to one of the categories in it. Okay, let me just give you the final value. 2 over 3 times square root of 3 will be equal to 1.154. So it's bigger than 1, and as a result for the first system, for G1, we are expecting an overdamped response. So for G1, we will have overdamped case. For G2, let's do it quickly. Omega n squared is equal to 16, therefore omega n is equal to 4. 2 zeta omega n is equal to 8. Omega n is equal to 4, and therefore zeta will be equal to 1. And since it's equal to 1, we are expecting a critically damped response. And finally, for the third case, G3, omega n squared is equal to 20, and 2 zeta omega n is equal to 8. 20 is indeed 2 square root of 5. And therefore zeta will be equal to 8 over 2 times 2 square root of 5, or 2 over 5 times square root of 5. If we get the exact value, we will have 0.89. So zeta will be equal to 0.89, and as a result it will be the system will give us an underdamped response because zeta is smaller than 1. So here we will have underdamped case. Alright, so that's all that we have for the, let's say, classification of the second order systems based on the values of the value of the zeta. When zeta is equal to 0, we have undamped, zeta between 0 and 1 underdamped, zeta equal to 1 we have critically damped, and zeta bigger than 1 we will have the overdamped case. Over here we have a summary of how the step response of the second order systems will look like based on the value that we have for the zeta. And this gives us a general form, a general understanding of what should we expect, yeah? Looking at the transfer function that we have for a system, how the step response will look like, and if we have the step response of a system, we can guess the kind of the second order system that we have. So basically for our system, when we have the g of s in the form of omega n squared over s squared plus 2 zeta omega n s plus omega n squared, the poles of the system will be located at minus zeta omega n plus minus omega n times square root of zeta squared minus 1. Then, based on the value of zeta, we have 4 cases as we just discussed. When zeta is equal to 0, the two poles are located on the imaginary axis on minus plus minus j omega n, and the undamped response is in the form of a similar to a sinusoid one. Yeah. Then for zeta between 0 and 1, we have the underdamped case. Two complex poles are given in the S-plane. You can see the values for the real part and the imaginary part of the poles, and the kind of the response that we get for the system has some oscillations right at the, let's say, beginning, and after a while those oscillations will be decayed, and as a result we will have the final value at some point. When zeta is equal to 1, we have two poles right at the same position minus zeta omega n, and you can see the critically damped response for the system. And finally, when zeta is bigger than 1, we have the overdamped case. For the overdamped case, we have two distinct poles on the real axis with negative values, of course, and you can see how the step response looks like. One important thing to consider is that we have considered values of zeta starting from 0 going to plus infinity. If you take negative values of zeta into account, you will end up with unstable system, and over there we just don't, we are not interested in the shape of the responses in general. Alright, so that's all for this lecture. We'll continue with more detailed analysis of the step response of the second order systems in the next lecture.